Hi everyone, welcome to the second lecture of this last module where we are discussing about different sensors for healthcare applications. In the previous class, we discussed about different glucose sensors, including some enzymatic and non-enzymatic electrochemical sensors, and then we started discussing about optical glucose sensors. Okay, optical glucose sensors, we have seen that they detect glucose by measuring change in the optical properties when glucose interact with the light. Okay, these properties are which it interact with the optical say light source is based on different mechanism. Okay, so if it is based on absorption, we have seen that there can be two kind of spectroscopy. One is the NIR spectroscopy and another is MIR spectroscopy, which is the mid infrared spectroscopy. We have also seen that these optical glucose sensors can also utilize scattering principle, where we have devices based on tomography or kind of imaging, which is known as OCT, optical coherence tomography. We can have devices based on rotation of polarization. Okay, so based on this we have polarimetric kind of glucose sensor. Based on emission, we have mostly fluorescence based devices, and based on the diffraction we have holographic sensors, right. We were discussing the near infrared spectroscopy, which comes under of course the absorption based optical glucose sensor, and we have seen how this NIR spectroscopy based devices work and what are their advantages and what are their limitations, right. So in the limitations we talked about 4 different limitations of NIR spectroscopy based glucose sensor. First was the low selectivity, the signal interferences, which is because of the variation in the skin tone, hydration and different level of temperature. Okay, the another disadvantage we have seen is associated with the requirement of complex multivariate calibration models for this NIR spectroscopy, and then the penetration depth, which is limited by the tissue penetration. Okay, some of the answers we discussed that can be given by the MIR spectroscopy based devices. So let us discuss the MIR spectroscopy based optical glucose sensor, which is somehow similar to the NIR spectroscopy based devices, but of course the wavelength and other things required here is a little different, and altogether it is again based on the absorption phenomena. So kind of similar working, but since we are using different range of infrared, there are slightly changes. Okay, so in very similar to the NIR spectroscopy, we have MIR light source. Okay, so this MIR source emit light into the sample. This sample can be skin, it can be interstitial fluid, or it can be blood, depending on what kind of device you are utilizing. It is non-invasive or it is minimally invasive. Okay, the glucose molecule absorb certain specific MIR wavelengths, and accordingly there are changes. Okay, so the transmitted or reflected light is analyzed using a detector, as you can see in this figure. You have MIR source, you have a waveguide or the ATR through which this light propagates. Okay, of course it is reflected or transmitted, and the detector, which is mostly in the form of kind of photo detector or the sometime it is thermopile. Okay, we have already talked about thermopile in more detail earlier. Okay, so this light is analyzed using these detectors. Okay, and based on the absorption spectra, you can calculate the glucose concentration. So basically this glucose concentration is governed by a law which is known as Beard-Lambert law. Okay, Beard-Lambert law, if you have not came across this law earlier, is a very simple law which states about the absorbance of a solution. So it suggests that the absorbance of a solution is directly proportional to three things. One is the concentration of the absorbing species, the path length of the light which is passing through the medium, and the molar absorbability of the species. Okay. So mathematically the same thing can be denoted by this equation, where this absorbance which is a unitless quantity is equal to the molar absorbability, okay, this epsilon, okay, multiplied by the concentration, okay, and the path length. Okay. This is the path length. Usually if you are doing it in the closed ambient or in the laboratory environment, this path length is the length of the qubit. Okay. So qubit is kind of cuboid kind of structure where your sample is loaded. Okay. It is very common in spectroscopy technique, including the UV spectroscopy, ultraviolet spectroscopy. Okay. So the spectral range that is utilized in this MIR spectroscopy is about 2.5 micrometer to around 18 to 25 micrometer, and the wave number associated with it is around 4000 centimeter inverse to 400 centimeter inverse. At the same point, it should be noted that in the glucose molecule, which is of course made up of carbon, oxygen and hydrogen, okay, the CO stretch is the vibration in the MIR is associated with 1030 to 1080 centimeter inverse wave number. The OH bending is associated with 900 to 1200 centimeter inverse, and the CH stretch is associated with around 2900 to 3000 centimeter inverse, and all this wave number is available in the spectrum range of this MIR spectroscopy. Okay. So you have, because of this, you have a strong and specific molecular absorption fingerprints. Okay. So glucose has this well defined absorption, as I have already mentioned. Okay. And based on this, you can have a number of spectroscopy based on this this MIR. Okay, you can have a transmission spectroscopy. You have ATR spectroscopy that we have just seen, which is attenuated total reflectance spectroscopy. You have photoacoustic spectroscopy. Then you can have a Fourier transform MIR, which is mostly covered under FTIR. Okay, and then in the modern scenario, you have quantum cascade laser spectroscopy, which is kind of tunable MIR. Okay. There are a number of advantages of this MIR spectroscopy. Of course, please note that it's very difficult to discuss all this spectroscopy in detail, but in one course or another, you will definitely come across this spectroscopy. The same thing can be applied for the detection of glucose molecule. Okay. The advantage of MIR spectroscopy are like you can have a direct molecular detection. Okay. So there is no specific reagents involved, including the catalyst or including the enzymes. Okay. So you do not need any external reagent, you can have direct molecular detection. Okay. It has potential for non-invasive continuous monitoring, although mostly these are minimally invasive devices, but then it has a potential of non-invasive continuous monitoring. Okay. And they have high specificity for glucose molecules because of the wave numbers associated with the vibration and stretching of the different bondings, including the CO, CH and other bonds. Okay. Then we have certain limitations also associated with this MIR spectroscopy based optical glucose sensor, including the strong water absorption limitation because of the spectra of water available in the MIR region. Okay. We have seen the same thing for NDIR sensor, where we have a strong background spectra of water molecules. Okay. Calibration is needed for a specific patient, and this calibration is mostly done using invasive technique. So you have to first calibrate your MIR spectroscopy devices using a electrochemical sensor, which is, I have mentioned, is a gold standard. So ultimately, even you are using a non non-invasive or minimally invasive device, but then for calibration you are requiring an invasive technique. Okay. Then the sensitivity is affected by variation in the temperature, the skin thickness and the hydration level of the skin. Okay. And the hardware requirement, the optical hardware requirement in case of MIR spectroscopy is little complex as compared to other optical devices. Okay. But then it also provide a lot of advantages. So MIR spectroscopy is considered as a good option for glucose monitoring. Okay. So this is all about the absorption based optical glucose sensor, but we have seen that we can use a number of mechanisms for detecting glucose, okay, including the scattering. Okay. So let us see scattering based optical glucose sensor, and we have seen that mostly the scattering based optical glucose sensor is used for kind of imaging which is known as optical coherence tomography, OCT. Okay. So the optical coherence tomography, the OCT based glucose sensor uses low coherence near infrared light to non-invasively probe the biological tissues. Okay. Usually typically a few hundred micron of skin, I mean beneath around 100 micron skin it is detected. Okay. The core component of a OCT device, the optical coherence tomography, is a interferometer. Okay. We have already seen the Mach Zehnder interferometer in one of the sensors application. Here for OCTs we use mostly the Michelson interferometers. Okay. The idea is light from a broadband low coherence source is split into two different arms. One arm is known as sample arm and another arm is known as reference arm. Okay. So the light from a broadband low coherence source is split into two arms, the sample arm and the reference arm. From the sample arm actually it hits the tissue under which it has to measure. Okay. And the reflected light from both the arms are recombined and creates an interference pattern which is analyzed by the system. Okay. In the tissue, OCT measures the intensity of the back scattered photons as a function of depth, creating high resolution cross sectional images. Okay. And that is why its name is not optical coherence spectroscopy, but its name is optical coherence tomography, because you are creating kind of cross sectional images using the back scattered photons. Okay. This allow specific targeting of vessel rich layers, for example the dummies for glucose assessment. Okay. That is why mostly target 100 micron or a little higher than that depth under the skin. Okay. The glucose in blood and interstitial fluid changes the refractive index and optical scattering properties of the tissue components, and there is a direct link between the glucose concentration and the tissue's scattering coefficient, and more glucose generally reduces the mismatch in the refractive indexes while reducing the scattering, and optical coherent tomography utilize this idea exactly. Okay. The system focuses on analyzing the slope and the attenuation of the OCT back scattering photon signal at specific tissue depth, which correlate with the changing or fluctuating glucose concentration. Okay. So precise measurement in the range of 200 anything basically above 100 till 600 micron depth, which is basically our lower dummies, maximizes the sensitivity of this OCT devices. Okay. As this particular zone, the 200 micron to 600 micron zone reflect actual blood or in some cases interstitial glucose level. Okay. A number of advantages are associated with the OCT, and kind of laboratory grade industrial grade devices exist on the OCT principle. These devices are non-invasive in nature, and it's a label free device. Okay. High resolution and real time imaging is possible. You do not actually penetrate a skin, you are basically using a light source for this kind of penetration. So basically no invasion is required, and they are capable of monitoring tissue microstructure along with the glucose level. So both the things can be done together. Okay. However, this OCT devices has certain limitations, like OCT glucose sensors need individual initial calibration with invasive glucose measurement to ensure accuracy, and it highly depend on, or it highly correlate with the patient. Okay. So if you have n number of patient, actually you need n number of initial calibration, and this is of course because of the variation in the optical properties of the skin of different patients. Okay. So you require a lot of calibration if you have a number of patients. Okay. So then there are other disadvantages also associated with the OCT devices, like differences in the tissue composition and glucose concentration gradients limit the detection sensitivity to certain depth level of the skin. Okay. Therefore, as I have mentioned, it is mostly confined to the laboratory ambient, but then if you calibrate it properly initially, these devices can be very accurate, and if the person is suffering from certain skin related or some tissue related anomalies are available in those patients, I think both the tissue anomalies as well as the glucose level can be monitored, and that can be the biggest advantage of this kind of tomography. Okay. Then we have devices based on rotation of the polarization, which we call polarimetric optical glucose sensors. As we know that these glucose molecules are chiral molecules, therefore they can rotate the polarized lights. Okay. So this polarimetric optical glucose sensor exactly use this idea. Okay. The basic polarimetric optical glucose sensor, as the name suggests, based on change in, or the rotation in the polarization. So there are 5 different components in the polarimetric optical glucose sensor. You have a light source which emit plain polarized light. Okay. Then you have the step of sample interaction, where the light passes through a glucose containing fluid. Okay. Then we have optical rotation, where the glucose molecule in this fluid rotates the polarization angle of the plane polarized light which was emitted by the light source. And then we have polarimeters, which are basically the detectors which measures the angle of the rotation. Okay. And then you have the other electronics like signal processing to convert the rotation to glucose concentration, and it utilizes this equation for the measurement, where this alpha, the observed rotation, is equal to the specific rotation of the glucose, which is around 52.7 degrees Celsius, for example, for D glucose, into the path length and the concentration. Okay. And it is it has been derived, of course, from the Lambert's Beer law that we have just seen. Okay. The advantage of this polarimetric optical glucose sensors are they are non-invasive again, or it can be minimally invasive. Okay. They have high specificity to the glucose molecule due to their optical activity of this glucose molecules. Okay. The continuous and real time measurement of glucose is possible. You do not have much devices which can monitor the continuous glucose. Okay. And since there is no enzyme associated with these devices, there is no enzymatic degradation. Okay. There are certain limitations also associated with this polarimetric optical glucose sensors, like they require precise alignment of optical components, because the rotation of this polarization requires, so that has to be detected precisely, otherwise you may not get the exact result. So you require precise alignment of different optical components, including the light source, polarizer, and other things. Okay. The sensitivity, I mean, these devices are sensitive to temperature and if there are other chiral substances in the blood. Okay. We know that there are several other chiral molecules available in the blood, so they can have significant amount of interference they can pose. Okay. Signals can be weak if the glucose levels are low. Usually it is not that high, so mostly you need kind of amplification before the signal can be analyzed. Okay. And then calibration needed for biological matrices, including the interstitial fluids. Okay. Then we have emission based optical glucose sensors. This is another type of optical glucose sensors. Okay, emission based optical glucose sensor detect glucose by measuring change in the emitted light, and this change in the emitted light, I mean to say, mostly in the terms of fluorescence. Okay, I hope that most of us know what is a fluorescence. We have studied this concept in lower classes. Okay, just to recall that, I will say that fluorescence is a type of luminescence only when a certain molecule absorb photons which excite their electrons to a higher electronic energy state, and further these molecules emit light as the electron return to the lower energy state. The emitted light has of course a longer wavelength or lower energy than the absorbed light. Okay. So, the fluorescence based optical glucose sensors can have based on this fluorescence can have a number of steps. Typically 5 different steps are involved. The first is the excitation or excite, then interact, emit, detect, and then quantify. It is as simple as this. Okay. So, what do you mean by the excitation or the excite? Okay. This fluorescence sensors as other optical sensor contains a light source. This light source, we have seen that mostly it is based on LEDs or laser. Okay. This source emits light at a specific wavelength which is aimed at the surface area on the sensor's area. Okay. This light is specifically chosen to match the absorption wavelength of the fluorescent molecule, which is known as fluorophore. We will be using this fluorophore word regularly. So, please note that this is nothing but a fluorescent molecule embedded or on the sensor. Okay. So, the light which is emitted from the source is falling on the fluorescent molecule which is known as fluorophore, which is embedded in the sensor surface. Okay. So, when this light hits this fluorophore, the molecule absorbs the energy and is elevated to a higher energy state that we have just seen in the case of fluorescence. Okay. The second stage is the interaction. Okay. So, usually these devices are based on enzymes, or these are enzymatic devices. So, usually an enzyme, mostly the glucose oxidase, is attached to the fluorophore. Okay. When the glucose binds to the sensor through these enzymes, it causes a change in the local environment of the fluorophore. These changes can be in the form of change in the pH or the generation of some byproducts like H2O2. We have already seen in the case of electrochemical sensors that gluconic acid was forming and H2O2 was also forming along with it. Okay. So, you can have these changes in the form of pH change or in the form of another byproduct in the form like H2O2. Okay. So, these changes affect how the fluorophore behaves when excited. Okay. So, it can be, the fluorescence can be quenched or it can glow less, it can glow more brightly, or it can change the color during this glow. Okay. The third stage is the emission. So, after excitation and the glucose interaction with the sensor surface, the fluorophore releases the absorbed energy, and this is done usually by emitting light at a different wavelength, which is nothing but the fluorescence. Usually this wavelength is longer because the energy emitted is smaller. Okay. The fourth stage is the detection stage, where a photo detector, it can be a camera also, or it can be even a optical fiber probe also. Okay. Collect the emitted light from the sensor. Okay. Mostly we use filters to ensure that only the emitted light is measured for accuracy. The amount, color or timing of the detected light is directly linked to the change caused by the glucose concentration. Okay. The final stage or the fifth stage in this fluorescence based optical glucose sensor is the quantify. Okay. So, the system uses calibration curves to translate changes in the fluorescence properties into actual glucose concentration values. Okay. So, the idea is very simple, to use a fluorescence which is happening because of the interaction of light with this fluorophores, okay, in the presence and in the absence of glucose molecule. This kind of devices, although looks very simple, but it poses a number of advantages. Okay, it can detect small changes in glucose concentration because of strong signal amplification associated. Okay, the fluorescent reactions is usually very fast in the range of nanoseconds, okay, which enables real time monitoring of glucose. Okay, it can be adapted even for wearable or for the implantable devices. Okay, they are compatible with the microfluidic and lab on chip platforms. Okay, they can detect multiple analyte using different fluorophores, okay, at the same time. Okay, fluorescent dyes degrade under prolonged light exposure, and this is the biggest limitation of fluorescent based devices, okay, or any other technique where you use this kind of dyes. Okay, so mostly these fluorophores are in the form of dyes, and they actually degrade when you are exposing it to light. Okay, there are other disadvantages also, like the signals can be affected by change in the temperature or change in the pH value or the change in the ionic strength or even change in the oxygen levels. Okay, the biological environment can degrade sensor materials or the recognition element. Okay, they require a frequent recalibration to maintain accuracy, and this requirement is continuous over the time. Means you do not think that you have a fluorescent sensor, you have calibrated it once and it will not require, it will keep on demanding the calibration. Okay, so tissues and biological fluids can produce even background fluorescence, and this can easily interfere with the readings. Okay, some fluorophores, particularly the quantum dot based fluorophores, can release a toxic component after this interaction, and these fluorophores require precise immobilization and encapsulation technologies, which is very similar to the electrochemical sensor, where we need to immobilize these enzymes at the surface of the working electrode. Okay, therefore, people has started looking for other kind of optical glucose sensors also, and then they have come up with another kind of glucose sensor which is based on the diffraction phenomena, and these sensors are known as holographic glucose sensors. So this holographic sensor, any kind of holographic sensor, basically uses holographic gratings or films as a sensing material or as a sensing element. Okay, they work on principle of volume holography or based on Bragg's diffraction. Okay, they detect glucose induced changes in the refractive index or swelling of the polymer matrices. We will see how this swelling happens. Okay, so if you are not aware of holography, holography is a technique that record and reconstruct the complete wave front. When I say complete wave front, I mean to say the amplitude and the phase of light using the principle of interference and the diffraction. Holography is a complete area of study in the optics, so it's not easy to detail each and every bit of holography, but if you are interested in this particular technology, I will suggest that you look at the good book on optics. Okay, so holography is a technique which record and reconstruct the complete wave front, including the amplitude and phase of a light using the principle of interference and the diffraction. Okay. Volume holography is a technique where, of course, it's a type of holography in which the hologram is recorded throughout the volume, or when I say volume, I mean to say the thickness of a photosensitive material, and it is not only restricted to the surface of the material. Okay, and that's why it is also known as Bragg's hologram or volume holograph. Okay, so then Bragg's diffraction, I am sure that you are aware of. We will just utilize the concept in this holography based glucose sensor. So, when waves are reflected from different atomic planes in a crystal, constructive interference occurs when the path difference between the wave is an integer multiple of wavelength. This is the popular Bragg's diffraction law, and the equation, mathematical equation is n lambda equal to 2d sin theta, where n is the order of diffraction and lambda is the wavelength of the incident wave, while d is the spacing between atomic planes of the crystal and theta is the angle of incidence with respect to the crystal plane. And we know that this Bragg's diffraction is the backbone of many different technology like X-ray diffraction. Okay, so it exactly utilizes this Bragg's diffraction and volume holography. Okay, so glucose basically diffuses into different hydrogels that are utilized for these applications. These hydrogels are already containing some boronic acid kind of receptor. Okay, so this glucose molecule binds with these receptors, and this causes swelling or shrinking of the hydrogel polymer matrix, which changes the refractive index, and this changing refractive index shift the Bragg's wavelength, and then because of that we have a optical response which is red. Okay, this is how holographic glucose sensors in nutshell work. Okay, there are various advantages associated with the holographic sensors, like they have high sensitivity due to the optical amplification associated. Okay, they are potential for non-invasive or minimally invasive monitoring of glucose level in blood as well as in the interstitial fluids. Okay, label free detection technique, you do not use any labels. Okay, they are compact and low power consumption devices. Okay, however they also have certain limitations, like it can have a good amount of interferences from other analytes. Okay, there can be some issues with long term stability of holographic film because it is based on swelling of the photosensitive film. Okay, then the calibration and the optical alignment are very complex for this kind of sensors. Okay, so this is basic idea of glucose sensor. I think we have discussed in detail about two different techniques for glucose monitoring, which is very popular. One is the electrochemical and another is based on optical, although we have seen that there are other glucose sensors also available, for example based on piezoelectric, but mostly these two techniques are very popular in healthcare sector. Okay, so what we will do is we will discuss about other sensors in healthcare, like ECG, the pulse oximeters and MRI in coming lectures. Okay, thank you.